Okay. So today, so a quick update. I didn't get homework from quite everybody. There's a couple people who I emailed specifically. Crap bag, hi. I hope that's actually one of our students and not just some person. Hi, who has just joined? Okay. So, sorry, I lost my train of thought. Yeah, so the last homework we've had, several people didn't hand it in. I've extended, I'm putting extensions on that. Similarly, what I'll do for the last homework is it's nominally due Friday, but if you get it in, but it's okay if you get it in late. And basically, you can have a homework extension until the exam day, basically. And I will send out the solutions once you have submitted or once you have told me you're not going to submit a homework. That way I don't have to have strict homework deadlines. I would appreciate if you got the homework done by Friday. That way I can talk about all the solutions on Friday. And Friday I've sort of set aside as a mostly review day. I might talk about a few things to wrap up the course on Friday, but largely I'm going to make that a day for everybody to ask questions and for us to go over some problems or whatever. And so I'll remind you that, and those things, I'm not going to prepare a lot. I'll prepare a few things and I'll have some things I can talk about if nobody wants to ask questions, but largely that'll be for you guys to do. Okay, so where we were last time we were talking about the properties of light, which we know is an electromagnetic wave. An electromagnetic wave happens because you have, let me share screen. Let's do, no, I don't want that. Come on, share screen, advanced, second camera. Okay. So you have light, which is a wave that's traveling through space. For instance, here's a position, and over time the wave evolves. And there's also, we know, a magnetic wave that goes near it, that goes with it, that's also traveling along at 90 degrees. And we talked on the first day, we talked a lot about how the orientation of this electrical thing and how that lends itself to talking about polarizers. And then last time we talked a great deal about the wave-like nature and how if I have two slits, they'll have waves coming out of them, and those waves will add or subtract from each other when they hit a screen over here, which creates light and dark places on the screen. And that is, you get two slit interference effects, which is one of the reasons we know that light is a wave. Okay, so today what I want to concentrate on are not wave-like behaviors, but on other behaviors that light have. Now, all of these things come from light being a wave, but they could have come other ways as well. For instance, the fact that light slows down in different media could be something like a bullet slows down when you fire it through liquid. So it doesn't prevent light from being a particle. So these things come from wave-like phenomena, but they could also come from other things. So none of this is really evidence that light is a wave. So firstly, let's just take a simple case to talk about this, right? So let's say I have a light bulb that's glowing, right? So the light, what this is doing is it's generating waves. And so you can think about this as a cork bobbing up and down in the water. It's generating circular, or in the case of light, spherical waves that are coming out. Another example here would be a speaker that I put in the middle of a room, and there's sound waves that are coming out all around the speaker. So these waves are all traveling outwards over time. And of course, we know one thing that's happening is the amplitude is reducing because the energy is expanding over bigger and bigger circles and bigger spheres. So the energy is reducing, which is to say, if you're close to a light bulb, it hurts your eyes, and if you're far away from a light bulb, it doesn't hurt your eyes. And so this
you didn't set Chrome to unblock it?
So one thing you'll see, though, is that to the perspective of what we're going to talk about is, instead of talking about these wave fronts traveling outwards, another way of discussing how light is moving is instead to define a direction that's normal to the wavefront, normal to the crests, and say the wave is moving that way. That's the direction the wave is moving. And so if this thing is on for a long time, these waves are continually being emitted from the source. Really what we can think about, another way we can think about this is instead of talking about these waves coming out, instead we can talk about rays of light coming out from the light bulb, or rays of sound, or rays of waves if we want. So these things are a mathematical tool or a conceptual tool we can use to describe the motion of the light coming out from this thing. It's a straight line because, and these things will continue to be straight lines coming out from a circular source. Or it could be I have waves that have come through a hole. So let's say I have got a fairly big hole, so diffraction is something I don't have to worry about. And I've got waves moving along like this. Well, then I could describe this as a series of rays moving to the right, or pointing to the right, and this is a beam of light. And so that's how we tend to think about a laser pointer, right? If I have a laser pointer, it has a beam of light that's shooting out of it, and we can talk about it that way. So this ray model is something that we can use for discussing how light works. Now, it doesn't work for this circumstance, and it doesn't work for polarizers. It doesn't explain those things. But for a lot of phenomena we deal with, we don't need to worry about the fuzziness of light. We don't need to worry about the wave nature of light, and we can just talk about its geometric properties. And so this general topic is called geometric optics. So these rays sort of describe how light usually behaves, unless we set up a special condition where there's interference or polarization. So the basic rules we can have for light then is that light travels in straight lines called rays. Unless something happens to them. So if they're just traveling, if you just have some light in outer space or even in air, which is pretty close to outer space because there isn't much to air, a ray of light will just keep traveling for forever in that direction. Unless one of four things happen. And we're only going to talk about some of these for lack of time, really. But there's four things that can happen to this ray. One is it can be absorbed, right? So this is where you have light and it, say, hits a piece of black fabric and doesn't come and just goes away. So the material absorbs the light and the material warms up slightly because it's absorbing the energy of the light. And this is something that happens all the time, right? Is light gets absorbed. So I can't see the light directly if it's a lampshade in front because some of the light is being absorbed by the lampshade. Another thing can happen is it can be reflected. So light can hit a surface and bounce off of it. It can be refracted, which is when light moves into a second substance and changes direction. And this is going to be one we focus on today and tomorrow. I'm going to talk about these two. And the third one is scattered. So scattered light is a little bit like reflected light in that it encounters some substance and then moves in some new direction. And scattering, for instance, so if I have some rays of light going this way and I have some dust in the air, the dust can scatter some of those rays off. And in fact, this is the mechanism by which the sky is blue, is there's rays of light coming from the sun. So there's the sun, and the sun is shining rays of light. And so then here's the earth. And this ray, and we're down here. And so this ray of light encounters some dust or something in the air or air molecules. And so it scatters off this way. And so we see that. So the sun's over here. So if we look this way, we see the sun. So if I look this way, I see the sun. If I look this way, I'm looking up into the sky, and what I see is blue light. And it turns out the blue light scatters more than red light. So the red light will continue through, and the blue light will get scattered. And if I look at somebody over here, another place in the planet, the light that makes it through, the only light that makes it through is, well, I should use red light, is the red light. The blue light gets scattered out, and so they see the red light, and so they're looking at the sun. The sun's, to them, the sun's almost on the horizon. So that's why sunsets are red and why the sky is blue, is light gets scattered. So that's I'm just telling that little story because I won't have another chance to put it in anywhere. Scattering also happens in things like fog or or other situations where you don't, it's not clearly being absorbed or changing direction. It's where it's moving in all sorts of random directions. But these are the basic processes by which light can change, right? And all of which are important for understanding what's going on. So for example, a very simple phenomenon you could talk about for light then is a shadow, right? So let's say I have a light source here, and I've got some like hole in a piece of cardboard, and I've got the ground. So this could be the sun and a piece of cardboard and the ground, or this could be like a lampshade and the wall. So let's say there's a lampshade in the wall. So there's some sort of funny shaped lampshade and a light bulb inside, and we can trace the rays coming from right. So what I'll see is I'll see dark here, and I'll see bright, and this will be a bright patch over here. We're on the wall, right? So I've cast a shadow due to this and a shadow due to that, and the rays that just barely make it inside that boundary, they'll make light on the wall, and rays that are outside that boundary make dark on the wall. Now, as I discussed the other day, these shadows are actually fuzzy around the edges, and there's weird stuff that happens there because of diffraction. But we're just going to ignore that today because it's a small effect, and so we're just going to ignore diffraction effects and pretend that light travels in straight lines, which it mostly does in everyday work. So that's our ray model, right? That tells us how things work. Now, how do we see objects? I'm afraid I didn't have a chance to look at the warm-up answers today. I had a phone meeting earlier today, so I didn't quite get to it. I'm going to look at them a little bit later. So you guys were answering this, so maybe you guys answered this all correctly. I'll walk through it anyway. So what our eye does is it basically measures how much light there is and what direction the light is coming from. That's how you can think an eye is doing. So for instance, let's say I've got a pencil. All right, and here's the eraser on the pencil. And then I'm going to look at it from over here. So that's going to be my symbol for an eyeball. And what my eyeball sees is it sees some rays coming from the back of the eraser, and some rays coming from the head of the pencil, and some rays coming from the middle of the pencil. And by looking at what direction the ray is coming from, I can parse out that there's a pencil there. I see some light coming from this side, that's orange and looks like the eraser, and some light coming from this side, which is black and looks like the head, and some light coming from the middle, and it's yellow and looks like the middle of the body. And that's what our eye does. It does this, of course, in 2 dimensions, but it tells us where the light is coming from. Now, of course, these rays are actually coming from somewhere else. There's a light source in the room that's creating these rays, and they're bouncing off the object. But for the purposes of just thinking about the search thing, we can ignore that and just talk about the rays coming off the object. Now, one of the important points here that comes in, is very important when we start discussing lenses, which we'll probably just barely be able to touch given time constraints, is that there are many, many, many rays, right? So if I look just at the head of the pencil, there are many, many rays coming off of it, like an infinite number of rays coming off the pencil head in all directions. And some of them are seen by our eye, right? The light's going in all directions. Some of them hit the eye, and that's what tells us the pencil is there. Incidentally, if you ever go back and look at medieval descriptions of light and sight, they had a very different idea. And sometimes I even see this reflected when I do INST courses and stuff like that, is there's some notion that your eye does something to the object. In fact, there's some psychological studies that say that people will sometimes pick this model if you offer it as an option. That somehow something's going into your eye and something's leaving your eye and coming back to the object. There's some other projection. It's not. It's only things going into the eye. That's the only way sight works. Is rays of light enter your eye, and that's how you know the object was there. And we're going to have this thing. This is called an object. It's something that's giving off rays of light. One other thing about this, though, is if I look at these rays of light that are coming out and hitting my eye, one piece of information I get from these is how far away the pencil tip is if these two rays coming in from this pencil tip are at a wide angle, right? Then, sorry, let's do this again. So here's my pencil tip, and let's say I have two rays coming out and hitting the eye like that. Then I know that the pencil tip is pretty close by. But if my two rays were coming off like this and almost collinear, then I know that actually the pencil tip is quite far away. So if my eye can detect, right, the angle, the opening angle between these rays, that tells me how far away it is. And this technique is basically what you're doing if you look at something really close to your eye. So you bring your finger in really close to your eye. You can feel your eye change its focus. If you're wearing I'm wearing glasses, so it's hard. So if you bring your eye really fit, you can feel your eye changing its focus, and it can see your eye clearly, and it can't see the background clearly. And that's your eye adjusting to only accepting rays that are coming from close in, or rather only focusing those rays. And if you bring your finger out, you can see it again. And basically, this allows you to tell the difference between things that are close to your eye and things that are about a meter away from your eye. And you can kind of judge how close it is with one eye, even if you don't know how big the object is. If you have two eyes, of course, this gets a little bit better, because if I have two eyes, then I can use the angle at which the two eyes see the object, and the opening between the angle between these two things tell you how far away it is. If the object is very far away, then those two rays are almost parallel. And if the object's really close, then you kind of have to go cross-eyed to see the object. And this is what gives us most of our depth perception. But this is all just coming from the eyes being able to detect the direction of the rays. So if it can see directions of the rays from an object, and those rays are quite a large angle, I know the thing's close by. I know if it's far away, those rays are at a small angle. Okay, so the first thing we want to talk about is reflection. Reflection is pretty easy, right? This is the thing a mirror does. So if I have a piece of mirror, so this is the dull side and this is the shiny side on the left, and I have a ray, just look at one ray of light coming in, the ray of light will bounce off. And the rule for how it bounces off is that if I have a nice, flat, clean mirror, I know that this is going to be symmetric about this middle axis. That the ray coming in and the ray coming out will be at the same angles. Now, the angles we tend to use, one way that's sort of natural to use is you'd use the angle between the ray and the mirror, but that actually turns out to be problematic for a case I'm going to show you in just a minute. So the two angles we use is actually we draw this normal line, right? This is the normal to the mirror, and frequently we'll use like an n hat to describe that vector, right? But what we use is we tend to use this angle in here, which we'll call theta I, and we'll use this angle here, which is theta R. And so theta I is the angle of incidence, and theta R is the angle of reflection. So the angle of incidence, the angle of reflection. And very simply, the rule for reflections for a flat surface is that theta I equals theta R. And the angle of incidence equals the angle of reflection. So if it comes in at some angle, it comes off at some angle, which is actually one of these which actually exhibits a property that a lot of the rules of light have, which is that if I shine a light going this way at this point, it bounces off this exactly the same as if I shine a ray backwards along the same lines. If I shine a ray along this, it'll go back to the same point, that it's independent of direction. If you time reverse the whole thing, you get the same picture both ways. So that's, which is a general feature of light. Okay, so this is fairly straightforward in a case like this. How about a case like this? Who haven't I picked on lately? Caleb, I haven't picked on you in a while.
Oh, yeah. So if you look at it, it has to go like you could flip it flat so the mirror's flat. I think it's easier to look at it like that. And if it comes in, it has to go in at the one angle and then go straight out the other angle.
Mm-hmm.
So it has to be down and to the right. And it has to be 30 degrees from the mirror. So, and the mirror's already 30 degrees. So that's BC.
So you're looking at this angle here.
Yeah.
Yeah. So that's one way you can do it, is you know that this angle here has to be 30 degrees, so you know that this angle of the reflected ray. Right? Here's how you do it if you're using the normal line, right? So so this is exactly correct, right? It's down to the right. So the normal line is all going off in this direction, right? It's normal to the thing. And I know that if the angle is normal is 30 degrees between here and here, then there must be 60 degrees between here and here. That's the angle of incidence. It's 60 degrees with respect to the mirror, right? So the mirror's normal is that direction. So there has to be 60 degrees, and there's 30 degrees on this side, and this whole thing is 90 degrees between the mirror and the normal. So there has to be 60 degrees here. So that means there has to be 60 degrees in the reflected ray. So there has to be a total, here of 150 degrees, which leaves 30 degrees left on the right. It has to be going down to the right. If you answered downright 60 degrees, that's actually along the mirror, which is too far. So that would be a ray going that way instead of that way, right? So now, why are we using this weirdo normal thing? Well, because we might be dealing with non-flat objects. Oops, come on.
So wait, can you repeat again what the answer to the last one
That
was?
was that was C.
Oh.
You had. Okay, Stephen, you're pretty quick off the mark there. Why do you say D?
So I said D because the initial laser beam that's coming in there, and the angle between the vertical and it are both 30. So then we know that half of that is 30, and then you add the other half, and it becomes 60.
That's exactly it. Yeah, that's really the fast way of thinking about it. And I think took everybody right. You have to see which angles are important, right? So I know this angle. So this is the normal, is what I've laid my pen on here, right? That's the normal to the surface at that point. It's pointing directly away from the ball. So the angle between the incoming ray and that normal is the same as this angle in here, right? Because this is vertical and that's at that angle, and this is vertical and that's at that angle. So this is 30 degrees here. So this is 30 degrees here. So the total angle between vertical and the direction of this ray is 60 degrees, which is the same as this angle over here is between vertical and that ray is 60 degrees. So there you go. So you get it. So this using the normal thing is important for this reason, because we have curved mirrors, we have parabolic mirrors. You might want to know what the light looks like coming off a doorknob. And so to do that, you'd have to model it like this. And of course, this is the calculation that's done in the computer when Pixar builds its movies, right? It's got these equations built in. It's in 3 dimensions, and writing down this equation in 3 dimensions is actually a little tricky for a computer to do it. But the basic idea is simple, and it's why we use that normal as being the thing that we're talking about. So it's the normal at the place where the ray hits the surface. Now, because of that, you can have surfaces that aren't flat, and we can deal with that problem now. So one problem you could deal with would be a bumpy surface, right? So if I had a surface that looked like this, right? One ray coming in might hit here and might bounce straight back. Another ray coming in from the same direction would bounce off and go this way. Another ray coming in from this direction might hit here and bounce off this way. And another ray coming in to here might bounce off and come off at some other angle. And so even though the rays coming in are all from the same place, this is like a beam of light coming from the window, let's say, this surface will have the rays bounce off in all sorts of crazy directions. And it's still behaving exactly like a mirror, but because it's bumpy, those rays are now scattered in random directions all over the place. Now this is how, yeah.
So is that why like water, when it's like wavy, that's why the images look all like messed up, is because the light waves are going all which way?
That's a little bit, but I'm thinking something even simpler than that, which is the piece of paper we're looking at. Right? So if I have some light coming like from a light bulb nearby, and you can tell the light bulb is sort of over there because of the shadows, right? The light is coming down and hitting the paper, and the paper is bumpy, right? And so this throws the light in every possible direction, some of which is headed towards the camera. So some of these rays hit the camera from this point, right? Boop, boop, boop. Some of these rays go off in all directions. Some of them hit my eye, some of them hit the walls, right? Most of them don't hit my eye, which is why looking at the paper is much less painful than looking directly at the light bulb. The number of rays that hit the paper and then make it to your eye is a very small fraction of the total rays. So there's rays coming off all these things. So that's how we perceive objects. That's how we see things. So this goes back to the pencil, right? If we have our pencil, should have a yellow pen. Maybe I can use a yellow pen in here. How about that? So I have my pencil, and then I have an eraser out here, right? The rays that are hitting the middle of the pencil, right? So I have rays coming in from the window or whatever. They're coming in and they're hitting the pencil, and some of them are bouncing off and hitting my eye, no matter where my eye is. So some of them are coming off and hitting my eye. Now, why does the pencil look yellow? It's because the light that we usually use, that we usually deal with in everyday life, is white, which is made up of all different wavelengths. The pencil absorbs all of those rays that aren't yellow. They stop and they get absorbed by the pencil. And only the rays that are yellowish in color bounce off of it and make it to my eye. And so that's how I perceive the pencil as being yellow in color. The brown stuff absorbs, the black stuff absorbs a lot of the light, not all of it, but a lot of the light. And so very little of it comes off. And so it looks like a very, very faint white light, which we perceive as black. And similarly with the eraser looks red because only red wavelengths are bouncing off the laser. Now, this is glossing over a whole bunch of color perception theory, which normally I get to talk about in this course, but we're not going to have time. But this gives you the basic idea of how we see things. Light comes in, possibly from a single direction, depending on what kind of light source we have. It bounces off an object in all different directions because of this, and gets us to here. These two kinds of reflection, so this kind of reflection where you have a flat surface, and it's basically where things look shiny, is called specular reflection. Specular reflection. This kind of reflection, where the rays bounce in all directions because the surface is bumpy, is called diffuse reflection. And every object basically has some combination of these two. In fact, there's a model called Phong, which kind of combines the two. And again, this is how Pixar makes its movies. It sees where the light is coming from and the lights in the scene. It figures out what the surface looks like and then calculates some combination of specular and diffuse reflection. If you look at very, very old CGI, like from the ages of Tron or very early video games, everything looks plain and angled and flat and shiny. And that's because the specular reflection is actually easier to calculate. The diffuse reflection is very hard to get right. And that's why modern animation looks different from earlier sort of simplistic computer animation, is because specular reflection was easier. And getting this diffuse reflection right is very hard. But that's basically the idea behind those things. So that's how we see stuff. Now, it's important to remember that reflection is a wave effect. And so one way you can visualize this is, so firstly, let's just start off with remembering what we saw about waves back when we were doing the waves chapter. So share screen, basic, go to this, right, is you remember that we had a wave on a string and it would bounce back and forth if it hit a wall, right? So if I had a surface that was not letting the wave in, the wave would bounce off and I might get a reflection or not, depending on what kind of hit I had. This would happen even if the object allowed some of the wave through. So for instance, this was going from a light rope to a heavy rope. You would see something like this, is the wave would come in through the light medium, hit the heavy medium, transmit some of the wave, but reflect a lot of the wave. And this would be the sort of thing is like if you were hitting glass. If you had light hitting glass, you can see a piece of glass because some of the light bounces off the glass and comes back to your eye. And so this shows you the transition between those. Or you could have a ray of light coming out of the glass and come to hit your eye. Now, you also see a reflection from that. And at night, if you're looking at a window, you can see the reflection from the inside of the glass and the outside of the glass. You can see both of those reflections. So you always see sort of a double mirror image when you're looking inside a lit house to the outside world at night. And you only see it at night because then you're not being swamped by the light coming in through the glass. So the same effect happens in 2 or 3 dimensions. And so I can sort of show you a little picture of that. So here's one picture of that working. So these are waves that are coming up from the bottom left, hitting a surface on the top, and then moving down to the bottom right. And so you can see these wave fronts marching from bottom left to top, and then from top to bottom right. And what's happening is that each bit of the wave is encountering that surface and then retransmitting. And when it retransmits, it transmits off in the other direction. And in fact, the wave doesn't know anything about the shape of that surface. All it knows is that it hits something and then re-radiates. And I can show you a picture of that. New share, advanced, nothing from second camera. Just let me, manual zoom. So imagine I had light coming from the top left, and that's the blue arrow. And so here's a wavefront. Here's a single line of crest. So you think about what happens when the crest hits this point right here at A, it starts re-radiating. It starts, so this is like a wave hitting a pier, and waves bounce off the pier, and they bounce off in all directions. So here I make a little bit later, there's a circle being made here from the rays that are coming off that point A. So here it hits point A, and here at point A, you can see this circle, this half circle here coming from the rays that hit there a little while ago. And now the wavefront's hitting here, and then the wavefront hits here, and then the wavefront hits here. So there's these circles of the reflected waves that are coming off each of those points. And then if you look at where the wavefronts add up, they add up along this line. And they interfere destructively in other directions and they interfere constructively in that direction. And so this whole thing adds up to a reflection of that wave. Now, thinking about it this way is incredibly hard. This is a very, very difficult model to keep in your head every time you're talking about light bouncing off an object. But the ray model basically encompasses all the same stuff. This just shows that under the hood, what's going on is actually kind of wavy and subtle, even though it's a very simple formula for us to work with in day-to-day life. Okay, so now we've discussed a little bit, we've discussed absorption, right? The rays can be absorbed by things. and we've discussed reflection. Now I want to discuss refraction. So now what we're going to talk about is what happens when a ray of light moves from one medium to another. Now, what is the medium for light? I always like to strike a happy medium.
Wouldn't that be air?
Well, that's true, but you can even have vacuum, right? Is light will travel through vacuum. That's how light gets us to us from the sun, is it travels through vacuum. So it can't be the air that's as being necessary. So light is a right? I can't do this. Everyone has their mics off, so I can't have you all shout at me. It's an electromagnetic wave, right? That's the major thing in this course. Whoop, 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 flashing lights, right? It's an electromagnetic wave. And now we know what that means because we know about electricity and magnetism. So this travels through E fields and B fields, right? And E fields and B fields interact with each other through Maxwell's equations, through the Faraday's law and Ampere's law, tell us how these guys interact with each other. But those laws involve these two symbols, right? This thing tells us how fast light travels in a vacuum. But this, for instance, is the permittivity of free space. No, the permeability of free space is this. And this tells us basically like how much a capacitor will polarize, how much what the electric field is in between two plates of a capacitor. But we know we can change this by putting plastic in a capacitor and put a dielectric in there. So we can change this to another value. That is to say, we can modify how light travels through a medium. And by doing that, and we remember that the speed of light is equal to 1 over root epsilon naught mu naught, that this is the speed of light is equal to this. If we change these values by traveling through a medium that, for instance, is polarizable, for instance, that electrons and protons can be pulled apart a little bit, then that allows you to change both of these numbers. And these numbers will always change in such a way that they get bigger. You can only make them bigger. You can always polarize or magnetize something more than nothing. You can't ever magnetize something less than nothing or polarize something less than nothing. So these numbers can only get bigger if you're in a material. So if you're in a material, these numbers get bigger, and so C gets smaller. So in any substance, you have some real value of light, which is or I'll call that the velocity of light. What we tend to use is we define C as being the speed of light in a vacuum. I always spell vacuum wrong. Oh well. The speed of light in a vacuum, and this would be the speed of light in some other medium. So light slows down when it enters another medium, okay? So now if we go back and we remember something about waves, we remember that the speed of a wave, or I'll use V for wave, is equal to lambda times the frequency, or if we prefer lambda over the period. That this is always true. This is sort of sets up the relationship between wavelength and frequency. Like the faster it moves up and down, the faster it moves up and down, the shorter the wavelength for a given speed. So if we're changing the speed of something, of the light as it's traveling through a thing, the frequency has to stay the same. So imagine I've got some waves traveling along, and they're going to hit a glass block. So we'll call this vacuum, and we'll call this glass. And we know the waves can travel through the glass. There's no problem with that, right? We know that it's transparent to light. It absorbs, that is to say, it absorbs very little of the light. So as these rays come up, if I think about what's happening right at this transition, so right there, so you can think about waves hitting the shore. At the shore, the water is moving up and down just the same way it was moving up and down back at sea, right? So if these guys are moving up and down like 1,000,000 times a second, then these guys will also be moving up and down 1,000,000 times a second, right? So then I think about what happens at that boundary. Well, this guy's going to re-radiate, and he's going to make So I'm going to re-radiate, and so a little bit longer, each of these circles will look like this, and that'll create a new wavefront. So the frequency has to be the same on both sides of the thing. If it's moving, because at any given place, it has to be moving up and down at that same rate. Nothing can make it move up and down slower. But since I've changed the velocity, I must be changing the wavelength. So what it must look like is if I've reduced the velocity, I must have reduced the wavelength. And so after the glass, these wavefronts should be close together. So this is the big and the small. Now, of course, when it gets to the other side of the glass, it reverts back to the first thing. So if we look at a piece of light looking through glass, we'll see the same color, right? Even if it's gone through glass or not. And there's no way of embedding your eye in glass or filling your eyeball full of glass or whatever. So this is not an effect you'll ever see. You can only see light that's traveled through something. So that's fine. Okay, so this is fast and slow and fast again. So, and one way to visualize this is you can think about each one of these wavefronts as a marching band, right? As a line in a marching band. So a marching band is running along, and the line, there's a spacing between each row in the marching band, and then they hit mud, and they can't walk as fast. Their feet stick in the mud, and so every time they take a step, they go less far. That's kind of how you can think of what's happening. So their steps all get smaller. So the rows bunch together as these guys run into each other. They don't run into each other, but they're far apart. And then afterwards, this guy slows down, so this guy catches up with him. And so they're closer together in here, and then they're far apart again when they're allowed to space out again. Or you can think about cars on the freeway. These lanes of cars here, and the cars all slow down and they speed up again. The spacings between them change because that's the thing. But they all have to stay in a line here. Now, what happens if I don't hit it dead on? And this is where it gets interesting. So let's say I've got a ray of light going like this and a surface, right? So what this means is I've got wavefronts that are perpendicular to my ray. So my ray is coming in like this. Now, it has to be that the lines on this side are closer together than the lines on this side. But it also has to be the case that the wavefronts don't break. And if I impose those rules, and I can do this mathematically a little bit later on, what that means is that these guys have to do this. Right? So if you think about our marching band, so this then looks like this. These all have to be right angles. I don't think I drew that very well. So if you think about our marching band, what happens now is, so a line of the marching band, some of them get to the mud and they start slowing down, but they're still in lockstep, right? They're still next to their partners here. So they slow down and they have to stay, this whole line has to stay continuous. And so as they slow down, what happens is they have to swing direction for this line to still connect to this line. So they swing direction as they go along until they're swinging entirely in a new direction as they go along. And so what happens is that if you go from fast to slow, it bends toward the normal. Where's the normal here? Here's the normal. So before I was coming in at quite a large angle with respect to the normal, and afterwards I'm coming out with quite a small angle with respect to the normal. So this is what's going to happen when I have this ray of thing. Now I haven't proven this to you. I can prove this to you geometrically, but the same effect can happen. Now let me switch here. New share screen. So here's the FET demo, and I'll do this in lieu of having any real object I can have. So here I've got a laser, and here's the laser beam coming from air on the top. So this is a fast medium on the top, and glass on the bottom, or water on the bottom. This is a slow medium on the bottom. Here, let me even make it more slow. So a couple of things to notice here. Firstly, there's a change in medium. And one thing that we know from looking at the ropes is that if I go from a light rope to a heavy rope, if I have a change in medium, I get some reflection from that and I get some transmission. And you can see that happening at the top. Some of the light is reflected. And this will happen if you have a piece of glass and you shine a laser at it. And you can play this with your laser pointer and your window. Some of the light will bounce off the glass and hit the wall on the other side. So you will get this situation. Some of the light, in fact, if it's glass, most of the light will make it through the glass, but it will bend in the glass and it'll bend towards the normal. You can move this guy around. If I put him at steeper and steeper angles, and let's turn him into a ray here so we don't have to worry about the width of that beam. So if I bounce him vertically, he goes straight through. And then if I change that angle, you can see that it always bends towards the dotted line on the bottom. And that effect depends on how much slower the other medium is. Now, if I change the other medium back to air, there is no interface. It's going equally fast on both sides. And so there's no bending of the rays. And so here, this is an air-air interface, which is to say it's just traveling through air. Or if it goes through two things that aren't very different, then there'll only be a tiny bending of the light. And there is almost no reflection in this case, right? Very, very small quantities of reflection if the two if the two media have got the same speed of light. This is actually kind of cool. I went out and broke one of my wife's canning jars the other day. Let me switch to share, advanced, second camera. So what I've got in here is a glass full of, maybe I'll show this to you on my other camera. So this is I've got some broken glass fragments in a beaker. And you guys can try this yourself. It's the demo I usually do in class is a little more dramatic than this. Let me turn off this light here. All right, so I'm looking at it upside down, but that's fine. And now what I'm gonna do is I'm gonna take some vegetable oil. Again, looted from the kitchen, because this is what I can do these days. If I pour the vegetable oil in, now you can still see the glass in there. It's not a perfect match, but it's very close. It's a lot harder to see, right? The shards on the top are very, very visible, right? Where it's sticking out of the oil, you can see that very, very visibly. But if you look down through the rest of the oil, you can barely make out some of the lines of the stuff, right? It's a very different picture above the oil and below the oil. And that's because the refractive index of the oil is almost exactly the same as the glass. I do this, and I did this in class. I do it with some slightly denser oil and with a glass rod, which doesn't have all the jagged edges, which are very easy to see. But with the glass rod just seems to completely disappear. This was actually the plot for the original Invisible Man, the H.G. Wells stories, The Invisible Man, written back in the early 1900s, was that he somehow changed how light traveled through him, so it was the same speed as everywhere else. So this has got the same speed of light going through the oil and going through the glass, and so you can't really see the glass very well anymore. Not very much light reflects off of it, and it doesn't bend when going through it, which you can see very clearly for the shard of glass that's above. Let me see, can I focus on that a little better? I always think that's cool. All right, here. The problem with this is you can all see each other, so I just saw Caleb second guess himself. So yeah, but this is pointing out an important thing here. So so clearly it's not C, right? Because if it was C, it would be not affected at all, right? Which of these rays is the normal to the surface? It's ray A. This is the one that's normal, right? So we know that this ray will bend toward the normal if it's slower. So C is not changing at all, and D is bending towards the normal. So B is the right answer here. Now D is actually bending away from the normal. Now this is what you would get if it was moving into a faster medium. It would do D. Moving into a slower medium, it does B. So if this was going from glass to air, if the blue were air and the white were glass, then it would do D. If it's going from air to glass, then it'll go B. It bends towards the normal in the slower medium. And so the right answer here is B, right? If we go back to change to the screen, right? So one thing I can do here, so for instance, if I make the bottom air and the top glass, now you can see what's happening. So now it's going from a slow medium to a fast medium, right? Slow medium, so short wavelength, fast medium, long wavelength. As it moves from a slow medium to a fast medium, you can see now here it's bending away from the normal. And so let's make it even more pronounced. So here, the angle on the bottom is bigger than the angle on the top. So this angle on the top is smaller than the angle in the bottom between the ray and the dashed line. Can you guys see my mouse? Am I moving my mouse around? Yeah? Okay, cool. It's not obvious. I get no feedback. Now, one thing that you'll see then is if I bend this ray off and I keep bending, right? The angle on the top and the angle on the bottom is getting bigger as the angle on the top gets bigger. And because the angle on the bottom is always bigger, I'm going to have to find a place where the angle on the bottom is almost 90 degrees and the angle on the top hasn't reached 90 degrees yet. Here it's only like 45 degrees. And if I bend this any further, there's actually no way for the light to escape. And what's happening here, this angle right here, as I make this transition right around here, is called the critical angle. And this happens only if if light is leaving a slow medium and going into a fast medium. In this case, there is no refracted ray possible. There is no way for those waves to actually stay in sync and make it out. There's no angle at which that allows you to do that. So in that case, they give up and all of the ray becomes reflected. And this is called total internal reflection, TIR. Total internal reflection is a case where if you have this circumstance, all of the light gets reflected. Now in a normal mirror doesn't reflect all the light. Some of the light gets transmitted and absorbed by the silver backing. Or if I'm looking through a piece of glass at night, I can see my reflection, but the reflection is very weak because most of the light is going through the glass. This is a case where all of the light gets reflected if you have this, which is a very useful circumstance if you want to keep light around. And the physical device we use that makes use of this phenomenon is a fiber optic cable. Fiber optics make use of total internal reflection to bounce the light around. How you can do that is, let me stop share, go back to the doohickey camera. So if, let's say I've got some glass or thick plastic that's bendy. And so outside here, this will be air, and inside here, this will be glass, or something with a high refractive index. If I shoot light into this, into the end of this fiber, well, and here this is at normal, so this will continue straight through without problem. What it'll do is it'll come along to here, and this is at a very, very fat angle with respect to the thing. So this is outside the total internal reflection critical angle. This angle in here is too big. And so none of the light leaves. All of the light bounces off that thing. So then that ray of light will come over to here, let's say. And then again, here's my normal, and it's again, as long as this angle is pretty shallow, all of the light will get reflected off and it'll continue down the pipe. As long as if I were to ever bend it like really hard, then, oh, that isn't inside the critical angle, so this guy would make it out, right? So this would be, if I twisted my fiber optic really, really hard, it would let it out. In fact, what you do around a fiber optic is you put a material around it that doesn't bend easily, that makes it stiff. But as long as I don't bend it too hard, I can put turns in it, and all the light that I put in at one end will come out at the other end with almost no loss. I'll have a little bit of absorption inside the glass, but not very much. And so this allows you to carry light many, many miles, hundreds and hundreds of meters, with almost no loss. And so, for instance, by pulsing this light on and off, I can send signals like Morse code. And that's how most of the internet works, is most of the internet works by information being carried through fiber optic cables, phone lines too. The last mile to your house, the last few miles will be done over a coaxial cable with just electrical signals being carried. But the bulk data transfer that's happening between, downtown Columbus and downtown Chicago will be happening through fiber optics, which are very cheap to make and extremely fast, because light is very fast and switching times are very fast for light. Those of you who are lucky enough to actually have fiber in your house will know that you get very good internet speeds from that. I don't. So that's why this is not a perfect transmission call. So this turns out to be a really important technological feature that you get, which is a result of this refraction phenomenon. Okay. Yeah, I think, let's see. Yeah, let me just define one. Let me just finish this discussion to get us done into the math a little bit. Now, let's say we have some velocity of light, which is different from the velocity of the speed of light in a vacuum. This thing is 3 times 10 to the 8 meters per second, which incidentally is about 1 foot per nanosecond. That's often that's how I characterize it, as is 0.3 meters is about 1 foot. And so if you do this conversion, it's about that far per nanosecond is how fast light travels, which is actually a very handy sort of thing when you're dealing with cable delays and trying to figure stuff out. Nanoseconds being 10 to the minus 9 seconds. If the velocity is different from that, it's convenient, instead of writing down all the velocities, to instead take the ratio. And so what you want is, you want a ratio that tells you C to V. And so we write it as C over V for the purposes of use. And we call this value N, which we call the index of refraction. This basically tells you how slow is it. So N equals 1 means vacuum, because that's where C is equal to V. And then for any other material, N is bigger than 1. And if N is, if N is very large, that means that you have a very slow medium. And this number is about 1.3 for water, 1.5 for glass. I think it's something like 4 for diamond, which is about as big as you can get and still have something work through it. So it's usually a number somewhere between 1 and 1.5, maybe 1.6. My glasses are made of high density plastic, which has a very high refractive index to weight ratio, which is why my glasses don't look like they're Coke bottles and falling off my face. And this determines how much the light will bend. The slower it is, the higher the refractive index, and so the more the light bends, which is the thing you can play with in that arrangement. Air, so N equals 1 is vacuum. N equals 1.0003 is air. So air does not slow down light very much. In fact, for the purposes of nearly any exercise that you'll ever do, is that these two numbers are so close to equal as we can just say they're same. We'll come up with a few examples where this might actually matter a little bit. Basically, air doesn't exist as far as light is concerned. So that gives you some sense of, oh, no, diamond is 2.4. There, I have it in my notes. So it never gets much above 2. Okay, so next time, we're going to figure out exactly what the angles are between the incident ray and the refracted ray, and then we'll use that to do some problems and to briefly take a tour of how lenses work and a few other minor applications to light. But we're basically at the end of this course. I'm going to do like one more lecture on getting this refractive stuff right, and then we're moving on. I'll remind everyone, the in-class lab is due on Thursday. We will cover all the necessary material next time on Wednesday. And of course, Dr. Robertson and I will be available through the lab sessions tomorrow to help you with the lab stuff. And you can of course do this reading, and there's nothing very difficult about Snell's law, so you guys can read ahead to get this. A lot of you have had this in high school. There's nothing in here which is very difficult. This is like the easy off-ramp to this course. Most people really enjoy optics because it's much easier than the other subjects. So we'll do that next time, and finish up with maybe some bigger ideas about where physics goes from here on Friday. So homework due on Friday nominally. If it has to be due later, let me know and we can give an extension. That's not a problem. Although I'd like you to try to get it done by Friday so you're doing this stuff this week. Lab time is tomorrow. Lab is due on Thursday, and our final exam is a week from Friday, I believe. So lots of time to get ready for that exam. Let me know if you have any questions or problems or comments or thoughts or worries. I'm always here and bored in my house. I want to be more bored. And I'll see you guys on Wednesday.
Well, time is our exam?
I think it's 10:15. I think it's basically the same as the class start time. I'll send around a reminder. See you later.